Hello and hi everyone. Here is chapter 3 part 1 angle modulation with Madam Hafiza. So here is the definition of analog modulation. So we have three types of analog modulation. The first one is AM, amplitude modulation, as part of chapter 2. And here we have frequency modulation, FM. Next is phase modulation, PM. Both are in same category, which is angle modulation. So for the definition, AM is the process of varying the instantaneous amplitude of carrier signal accordingly with instantaneous amplitude of information signal. And for FM, FM is the process of varying the instantaneous frequency of carrier signal accordingly with instantaneous amplitude of information signal. Lastly is PM. PM is the process of varying the instantaneous phase of carrier signal accordingly with instantaneous amplitude of information signal. Okay, for angle modulation application, because of its superior performance than AM, it is widely used for commercial broadcasting and for radio broadcasting and also for microwave and satellite communication system. FM is probably the most commonly used analog modulation technique, but PM is rarely used in analog system, but is very common in digital communication system. So here is the frequency modulation waveform. Okay, here is the information signal, our baseband. Here is the carrier signal that generated by the oscillator, and here is the output of FM. As you can see here, so the frequency of carrier wave is changed according to the information signal. So for the waveform of FM, the waveform that are close together here, alright, represent the peak of this information signal, while for the waveform that are more apart is represent the value of the sine wave. So here the phase modulation waveform, same goes like the FM. So here is the PM signal. So let me explain the waveform of PM. So the waveform that are close together represent the sine wave transition from negative to positive. Meanwhile, for the waveform that are spaced apart, represent the positive to negative waveform of information signal. And as mentioned in the definition, the phase of a carrier wave is altered according to the information signal, but the amplitude remain the same as the carrier. Here is AM, FM and PM waveform. So can you spot the difference between AM, FM and PM waveform? So here is the information, here is the carrier signal. For AM, is changing, the amplitude is changing instantaneously according to the information signal, but the frequency remain the same as carrier. For FM, here, okay, the amplitude remain the same, but the frequency now is changing accordingly with the information signal. Same goes to PM. So let's start with the angle modulation, a formula. So the angle modulation can be expressed mathematically as Vt equal to EC cos 2 pi FCT plus theta t. So here where Vt is angle modulated with EC equals to peak carrier amplitude in volt, Fc is the carrier frequency in hertz, and theta t is instantaneous phase deviation in radian. So for theta t is a function of the modulating signal, which is theta t equals to Fvmt, the modulating signal, where Vmt is equal to Em sin 2 pi Fmt, which is the modulating signal. So the choice between Fm and Pm depends on which one is directly varied by the modulating signal. So if direct Fm varying the frequency of a constant amplitude carrier signal directly proportional to the amplitude of a modulating signal, and for direct PM, it's varying the phase of a constant amplitude carrier signal directly proportional to the amplitude of a modulating signal. Once we use the direct FM, it is actually the indirect of PM. It's vice versa. For direct PM, it is one of indirect FM. So whichever properties is direct varied will cause the other property to vary as well. So here is a comparison of FM and PM modulation. So on your left side, the FM modulator is actually equivalent to this block diagram, which combination of integrator and PM modulator. And for PM modulator, it is actually equivalent to this combination, which is this combination of block diagram, which is differentiator and FM modulator. Okay, basically the mathematical for basic principle of FM, we have frequency deviation. Next, we have modulation index, and then the Bessel function, and lastly is the power analysis. So here, let's start with frequency deviation delta F. So relative displacement of carrier frequency compared to the original carrier frequency and the unit in hertz. So here is the frequency domain of information signal, and here is the information signal time domain. So in terms of frequency domain, here Fc minus delta F, which is represent the negative Vm. So the positive Vm is represent Fc plus Fm in terms of frequency. Fm is the process of changing carrier frequency by the modulating signal while the carrier amplitude remain constant. So as the modulating signal amplitude increases, the carrier frequency increases and vice versa. The amount of changing in carrier frequency produced by the modulating signal is measured in peak frequency deviation. Okay? Sometimes frequency deviation can also be expressed as maximum carrier swing, which is equal to delta F. So the deviation is proportional to the amplitude of the modulating signal. So frequency deviation delta F, peak frequency deviation can be calculated as delta F equals to KFVM in hertz. So where KF is the deviation sensitivity and Vm is the peak modulating signal voltage. So we can see that delta F directly proportional to modulating signal's amplitude Vm. So the deviation sensitivity Kf is a constant that shows the sensitivity of modulator frequency. So represent the input-output transfer of modulator with relationship between Vm and the resulting frequency shift delta omega in radian per second per volt. So Kf is equal to delta omega divided by delta Vm in unit radian per second per volt. It also can be written in unit hertz per volt. So given the Kf equals to delta F over Vm. So in short, it shows how well the modulator. So next is frequency modulation index, M. So the ratio of the frequency deviation to the modulating frequency is known as the modulation index, M. And M equals to, given the formula, M equals to Kf in radian per volt times Vm divided by omega m, and it is unitless. Or in terms of hertz, Kf equals to M equals to Kf in hertz over volt times Vm over Fm. And since delta F equals to Kf Vm, substitute in the M, we get M equals to delta F over Fm. So this M, the modulation index, is unitless or dimensionless. For the modulation index, here is M equals to delta F over Fm, and it also can be written in percentage, just time the 100. In most communication systems using FM, maximum limits are put on both the frequency deviation and the modulating frequency. Okay, let's try the example 1. Determine the modulation index for FM signal with the given of frequency modulating signal 10 kHz and deviated by plus minus 10 kHz. So, first of all, we write the formula. M equals to delta F over Fm. So, here is your Fm and here is your delta F. So, 10 kHz delta F over 10 kHz Fm is equal to 1, and it is unitless or dimensionless. The total frequency change we call as carrier swing is 2 delta F, and it's equal to 2 times 10 kHz is equal to 20 kHz. So let's try this example too. A cell phone transmitter has a maximum frequency deviation of 12 kHz. Calculate the modulation index M if it operates at maximum deviation with a voice frequency of 300 Hz. Here is your FM. And also 2500 Hz. Here is your FM. So write down the formula. M equals to delta F over Fm. So delta F is 12 kHz divided by 300 Hz. The answer is 40. And for number B, M equals to delta F over Fm. So delta F 12 kHz and the Fm is 2.5 kHz is equal to 4.5 it. So, end of part 1 with Madam Hafizah. Stay tuned and thank you.